All right, guys, today we're going to talk about Euler's method. Okay, this is one of the extra topics that we throw into the end of BC, and it's a pretty short lesson. It has to do with tangent lines. And so in AB, we talk about finding a tangent line and using that tangent line to approximate values on a function. Okay, well, what if we did a tangent line and we actually broke it in half and did another tangent line later on in the graph? All right, well, what happens with this is, here's a regular tangent line. If we were to recalculate the tangent line at a certain point on the tangent line, it would then change the direction and kind of get it closer to our actual curve. Well, what if we did that multiple times? Okay, instead of doing it just once, what if we did it 3 times? Okay, each time we recalculate the tangent line at those points and draw the line from there, it's going to get it closer to the curve, and the more accurate it's going to get. That's the Euler's method's all about, is getting these new tangent lines, so to speak, to get a better approximation for values. Okay, so the thing that we need to know is this formula. All right, y new minus y old equals m old, and yes, that spells mold, times x new minus x old. This is the key for Euler's method. Now, you guys got some problems in a packet today, and they're a bunch of old FRQ packets. So we're actually going to take a look at 1998, letter B. Okay, and so if you flip over to that page, it's the first one up there. It says, let y equal f of x be a particular solution to the given differential equation with the initial condition f of 0 equals 3. Okay, so they give us an initial condition of f of 0 equals 3. All right, they say use Euler's method starting at x equals 0 with a step size of 0.1. So start at x equals 0 with a step size of 0.1. That's essentially how often we're going to recalculate this tangent line. Okay. And we're going to use it to approximate .2. So we want to approximate f of 0.2 there. Okay. Well, the differential equation they give us is dy over dx equals xy over 2. Okay, so that's all we need to actually figure this out. We're going to start off with our first point, and that's our initial condition they gave us. The f of 0 equals 3. That gives us a point 0, 3. These are our old points. This is our x old and our y old. Okay. We're now going to come up with our new points. Now the step size is 0.1, so that's as far as we can go. So we're going to actually do 0.1 comma something. We're not really sure what that is, but this is going to be our x new and our y new. All right, so let's plug this into our formula here. Okay, we have y new, that's what we're going to look for, minus y old is 3, equals, we need the mold. That's our m old. Our m old is going to come from our differential equation and our old point. So that's going to be 0 times 3 over 2, which just gives us 0. So 0. And our x new is 0.1 minus our x old, which is 0. Okay, so we plug it all in, and really what we're looking for is our y new. So this one's pretty easy because y new just becomes 3. All right, so now that we have that y new is going to go into our point and now we have 0.1 comma 3. Well, this new point now is going to become our old point. And we're going to do the same process one more time, but this is our old, and we're going to use another step size. Our next step size, if we add 0.1, gives us 0.2. And notice that's what we're actually trying to approximate. These are going to be our x new and our y new. So we're going to do the same thing. We still need our mold. And our mold is going to come from our old point. So again, that's going to be xy. So 0.1 times 3 over 2, which gives us 0.3 over 2. So let's plug it in. Y new minus y old. Y old is going to be 0, or going to be 3, equals 0.3 over 2, our mold, and 0.2, our x new, minus 0.1, our x old. And here's the thing, we're trying to find an approximation for f of 0.2. Well, all we have to do to get that now, that's really what this is, our y new. All we gotta do is add the 3 over. So 0.3 over 2, 0.2 minus 0.1 plus 3. And on a free response, guess what? That's it. We would just leave it. And a lot of these do show up on free response questions, but they have also shown up on multiple choice questions. So sometimes we do have to simplify these out, but usually it's pretty generic arithmetic. All right. Let's go ahead and do one more example here before I let you loose and do the rest of them. We're going to go ahead and look at 1999B, which is right below it. So 1999B. All right, this time they give us the differential equation, f prime of x equals 1 plus e to the x over x squared. They give us the initial point 3,6, so you do have to go back and look at the problem a little bit here. And B says use Euler's method starting at x equals 3 with a step size of 0.05. So start at 3. Our step size is 0.05, and they want us to approximate f of 3.1. Okay, same thing. So let's go ahead and do our formula. Y new minus y old equals mold x new minus x old. Okay, so we got a 0.36. That is going to be our old point. And we're going to use one step size, so we're going to add that on there, so 3.05, comma, blank. That's what we're trying to find. These are going to be our news. All right, so let's plug that in. Y new, that's what we're looking for, minus y old, which is 6, equals mold. Well, we need the mold. So our mold, 1 plus e cubed over 3 squared, which is 9. Okay, so we're going to take that, put that in there, 1 plus e cubed over 9. And we have our x new, 3.05, minus our x old, 3. Okay. Thank goodness this is a free response question and we don't have to do any major simplifying. Our y new that we're looking for, all we got to do is add 6. So 1 plus e cubed over 9. All right, 3.05 minus 3, and I know hopefully you guys can actually do the math on that. There's our y new. So that's what is going to go right in there. Whew. So that's going to become our new old point. So 3.05, comma, 1 plus e cubed over 9, let's do the math real quick, 0.05 plus 6. So this is our old and our old. And our new, we're going to add another step size, which gives us 3.1, which, fancy that, that is our one we're trying to approximate here. So a lot of these, they set you up so that you hit that point within 2 or 3. Sometimes it does hit 3. And we know we're going to need our mold, so let's go ahead and find our mold here. 1 plus e to the 3.05 over 3.05 squared. Okay, so let's go ahead and plug everything in and see what we got here. So y new minus y old, so 1 plus e cubed over 9 times 0.05 plus 6, be careful with your parentheses, equals the mold, 1 plus e to the 3.05 over 3.05 squared times x new minus x old. And again, our whole purpose here is to solve for that approximation of f of 3.1, which is the y new. So all we have to do here is add this ugly thing over to here. So 1 plus e to the 3.05 over 3.05 squared times, hopefully everyone's okay, I'm going to make that 0.5 again, 0.05, and then we're going to add that over. So plus 1 plus e cubed over 9 times 0.05 plus 6. And that would be our final answer for part B. Now it does keep going. It says use f double prime to explain why this approximation is less than f of 3.1. And think about it, if you're using f double prime, we're talking concavity. And so if you go ahead and work that out, and I'll let you guys kind of do the work on that, but if you find out that the second derivative is negative, we know that it's going to be concave down. Remember, when you have a tangent line, even if it's taken multiple times, and you have concave down, it's always going to be less than the actual value. Okay, so try that out and see if you can prove that using that. But that is Euler's method, and that's typically what we see most of the time as an additional FRQ question. The homework with this is go ahead and finish out all the problems that deal with Euler method here. You'll notice that some of these are familiar to old questions that we've done in class when we did our slope fields. Now you're just going to go ahead and complete those with Euler's method.